Welcome to the iLearn Virtual Campus. Please sign up for a free iLearn membership on our website, check out our 7th annual conference coming next spring 2021, and let us know if you're interested in hosting events or leasing space on our campus by emailing campus@immersivelrn.org.
Hello everyone, my name is Stephen Young and today I'm going
Testing. Plain voice. Everyone can hear me? Okay. Hello everyone. Thanks a lot for being here today. We are going to begin our next technical session. I will invite Professor Gan Lee come here to begin the session. Professor, please.
Thank you very much, Francisco, for introduction. Hi, everyone. It's my privilege to be here and chair this session 12, which is on evaluating user experience. We have 5 papers to present in this session. And we'll begin with the first paper titled Virtual Reality Sickness Detection, an approach based on geological signals and machine learning. And the paper is from IRT-Become and Ubisoft, and the authors are Nicholas Martin, Nicholas Matthew, Nicole Palamin, Martin Ragot, and Jean-Marc Deverez. And the presenter is Nicholas Martin joining us here today. So we'll get started with the presentation and we'll have 5 minutes question and answer afterwards. So I'll invite Nicholas Martin to the stage while the presentation is played. Thank you.
Hey everyone, thanks you for joining us today. In today's presentation, I'd like to show you an experimentation on virtual reality sickness detection based on physiological signals and machine learning. This paper is the result of a research collaboration between Become and the Editorial User Research Lab of Ubisoft Paris. I will start with some elements of context. Virtual reality sickness remains a major limitation of virtual reality. It can be defined as the feeling of discomfort similar to motion sickness that could occur when experiencing virtual reality content. It is mainly due to discrepancy between the vestibular system and cyber sickness. In the following video, we can see one of the participant during the experiment. You can hear the beep, which rings every 40 seconds. It indicates to the participant that he must give his current state of cyber sickness. Here, he answers 5. To exploit the physiological data in order to detect cyber sickness, several steps are required. First, the data are windowed into fixed-size windows of data. The raw physiological data is not directly exploitable. It is necessary to transform them by extracting specific features. 50 features are calculated on each extracted window of data, 11 on the cardiac activity and 39 on the electrodermal activity. These features are based on the literature review in the field of cybersickness and more widely in the field of physiological computing. Then, as previous research showed an important variability between participants concerning the physiological responses, 2 methods of normalization have been explored. The first one consists, for each participant, to subtract the value of features during the baseline to the other features' values. The second one consists, for each participant, to add the value of features during the baseline to the feature map. The number of features in input is doubled. Based on the extracted features, the training of models are done. It is composed of 2 parts. First, the training aims to automatically infer the function between the input data, in this case the extracted physiological features, and the output data, in this case the subjective responses. Second, the testing part aims to evaluate the performance of trained models on new data. Several machine learning algorithms have been evaluated, but random forest provide always the best results on our dataset as in previous research with physiological data. So only results with this algorithm will be presented. Several training strategies have been tested to evaluate the approach and the performance of trained models. First, one model per participant has been trained. Second, one model trained on the data of all participants. Then, the generalization have been evaluated using leave one out cross-validation. These different training methods allow the performance of models to be evaluated in detail. Now, I will present the main results of the current study. First, the influence of the normalization method as well as the window size have been evaluated. The normalization NAF corresponding to the adding of features calculated on the baseline to feature map. It offers the best performance. The normalization by subtraction of features calculated on the baseline also improves the performance compared to no normalization. Even without normalization, the trained models performed better than a naive model. Second, the larger the size of the analysis window, the higher the performance. As previously explained, participants reported their state on a scale between 0 and 20. Nevertheless, as showed in this histogram, the majority of participants expressed relatively low level of sickness. So, several data split have been evaluated where subjective values are grouped into 2 or 3 classes. Trained person-dependent models and group models showed interesting accuracy performance. The recognition rate ranged from 85.9% to 91.7% according to the configuration and is better than a naive model. Nevertheless, the models failed to generalize to new user according to the performance with person-independent models. I will discuss in more details about this point after. Based on the trained model, we developed a real-time proof of concept of VR sickness recognition. Apart from the problem of generalization, the processing chain is suitable for real-time applications. Now, I will discuss some elements of our study. Results confirmed the interest of electrodermal and cardiac activities to measure cybersickness. Indeed, the feature importance calculated on trained models showed that both activities are relevant for the recognition. Features coming from other field of physiological computing seem relevant for cybersickness detection such as features on frequency domain of ETA. Moreover, machine learning seems adapted to automatically detect cybersickness. The approach is also suitable for real-time application. Nevertheless, two main elements need to be noticed. First, only relatively low level of cybersickness have been inducted to the participant, especially due to ethical and safety reasons. Second, the generalization remains a big issue. Only few papers explored this problem with physiological data. Currently, trained models are able to detect cybersickness only when data of the participants are available during training. In other words, the recognition performance is weak for new users. Normalization of the data improves the performance but didn't currently solve the problem. In conclusion, the current study showed that recognition based on physiological signals and machine learning is interesting when data of the user are available to adapt the model. But, the generalization remains a huge challenge. Thanks you very much for your attention. If anyone has any question, I'd be glad to try to answer them now or by email.
Thank you very much. Let's give pause for the presentation. Any questions from the audience?
Hello.
Hello. Yes.
Generally after people are getting used to VR, they stop feeling sick. That's very common. And because the system is better when you have already trained someone, couldn't it become obsolete if you have to train the person first, after they get sick, they stop getting sick later? I don't know if I explained well the question.
I have some problem with the sound, but if I correctly understand, the question is about the training of people to cybersickness to reduce the occurrence of cybersickness, or the training of specific model for each person, and after evaluate the model? I'm not sure that I've correctly understood the question.
No, I meant when people get to use it, when they play virtual reality for a long time, they
Yeah.
stop getting sick generally.
Yes.
And the model, it depends on training on that specific person. So after the model has been trained, isn't it likely that after a few turns it will become obsolete because the person will stop feeling sick?
We didn't evaluate that, but yes, probably because as the model have some difficulties to generalize to a new user, we can suppose that we have some difficulties to generalize to other states of the user. I think it's a very complex problem to be able to generalize to other state of the same user. We can't we don't have the possibility during our collect of data to collect the data on the same participant during several days. But I think even on the same participants, we have a lot of variability between days, and yeah, maybe the model becomes not adapted over time.
Thank you very much.
I think there is a question on FOBA. In the paper, the participants, it's a question from Tiago Chaves, by the way. Sorry, it's actually Hang Yuso. In the paper, the participants play different games. It's asking how do you choose the game for experiment, and do they cause the same type of VR sickness or symptom, or did you spread it out to different types of games, or how did you choose basically the games?
We chose the game. We work with Ubisoft on this project, and Ubisoft wants a system that's able to detect cyber sickness on the variety of games that it can produce. So to maximize the chance to be able to detect cyber sickness in all situations that they confront their participants, they chose the game with a variety of movements such as walk, flight, and we didn't evaluate the influence of the type of game on the cyber sickness level because for each individual, the effect is different. For some guys, we see that the movement of walk was very susceptible to generate cyber sickness, and for other participants, it will be to flight, for example. So we try to maximize the viability of type of movements to have the most possible viability on the data, and we chose the game like in this way.
Thank you. I think we might have one more question due to time. It's a question from Lee Bernstein. It's asking, what is the current state of automatically judging a particular application without any human data? I understand that you can't generalize this model, but are there published guidelines to avoid sickness?
I'm not an expert. I'm an expert on the physical computing, so I'm not on the cyber sickness. So I don't really know the current state of automatic evaluation of game or VR application. I'm sorry for that.
Just one quick question from myself. So how do you choose the sensor that you used, and is there any other sensors that you are trying to look into in the future?
Yeah, we chose the sensor with one particular elements. We need a sensor that we can use on the multi participants at the same time. So it had to be cheap. So it was the first element to choose it, and we tried at the same time to use a wearable sensor called Empatica E4. The results are very close than with the Scheimer GSR Plus. We at the time of the data collection, the eye tracker was not deployed as now in the HMD, but I think it's a very interesting sensor because we don't have to put it on the participants, and some studies show that it could be interesting to evaluate cyber sickness. We don't we make the choice to don't use a sensor that are too intrusive for the participants. So
Thank you very much. Thank you. Let's thanks again Nicholas Martini by a big applause. Thank you.
Thank you very much.
Okay, our next paper is from the University of Texas at San Antonio. The title of the paper is Automatic Detection and Prediction of Cyber Sickness Severity Using Deep Neural Networks from Users' Physiological Signals. And the authors of this paper are Rifatul Islam, Yonggan Lee, Murad Jaloli, Imtiaz Muhammad, Dakai Zhu, Paul Rudd, Yufei Huang, and John Quarles. And the presenter is Rifatul Islam. So I'd like to invite Rifatul to come onto the podium as the video is playing. Thank you.
Hello, everyone. My name is Rifatul Islam, and I'm a PhD student at the Department of Computer Science at the University of Texas at San Antonio. And today, I'm going to be presenting our work, Automatic Detection and Prediction of Cyber Sickness Severity using Deep Neural Networks from Users' Physiological Signal. So, cyber sickness can be defined as a set of motion sickness-like symptoms. More than 60% of the virtual reality user actually suffers from cyber sickness. So it's a major concern for the overall user experience in virtual reality. There are two major options to measure the severity of cyber sickness. One is the subjective measure. There are objective measures too, like collecting physiological data and then correlate the data with the severity or the verbally reported cyber sickness during the immersion. So one of the major problems with the typical approach that I just described. So one of the major problem is this whole process is not fully automated. What I mean by that is either you need human intervention or any kind of software intervention to collect this verbal feedback or the verbal data during or before and after the immersion. And that breaks the presence of the overall immersive experience. The other problem, one of the other major problem is that collecting the subjective feedback before and after the immersive experience doesn't give you sufficient granular understanding of the cyber sickness severity during the immersion. So we need something that is fully automated and that can detect the cyber sickness during the immersion. There are a couple of ways to do that. So I'm going to be talking about that. So motivated by that, our question is, can we really automate the process of detecting cyber sickness? And we're going to go a little bit further. Can we predict cyber sickness even before it happens? And if we can detect and predict, how can we automate this thing? And what is the correlation between the physiological changes with respect to cyber sickness? As it turns out, or any kind of distress that is happening to our body, either you feel dizziness, nausea, or physiological response reacts to that, or our physiological data reacts to that. So in the case of cyber sickness, our heart rate goes up and our GSR goes up, and the heart rate variability and breathing rate goes down. That is also reported by previous researcher, and we also found similar results. So based on this relation, we can basically propose a way to solve the automatic detection and prediction of cyber sickness. And if we can do that, then we'll be able to basically try to elevate the problem or elevate the discomfort during the immersion with some adaptive reduction techniques. So for our study, we actually recruited 20 participants, and the average age was around 24 years with a standard deviation of 2.75 years. And we used the roller coaster simulation, which was developed using Unity, and it was displayed using an HTC Vive headset. The roller coaster takes about 1 minute to complete a cycle, and there were like a maximum of 13 different cycles, and the person can quit at any point in time. And it was a seated experience. And we used two different sensors. One was the OmniSense heart rate sensor, and the other one is the Nilog galvanic skin response sensor. So the data collection step is pretty straightforward. So on figure 7, you can see that this is a stepwise illustration of the data collection. And figure 6 was an actual study setup. So we had actually a TURP on our floor in case someone throws up. So that almost happened in some cases. Okay, so the step was like we collected the demographic information, we set up the heart rate and the GSR sensor, then we collected the resting baseline data. Then the resting baseline data especially was like there was no virtual reality experience during that 5 minutes of resting baseline data. So we just wanted to collect the resting baseline of each one of those physiological sensors. And then we collected the resting VR data, which is basically exposed the participant into the virtual reality simulation, but they were not moving, and the roller coaster was like not moving at all. Then there's like 15 minutes of roller coaster simulation, and at the end of the study, we collected the post SSQ. And during that 15 minutes of roller coaster simulation, we actually asked the participant to rate their discomfort on a scale from 0 to 10. We actually used human intervention in here because we need a lot of data to label. We need a label data to actually automate the process. So we can basically use this pre-trained model later on without any human interventions. And this is a result for the SSQ. And from the SSQ result on table 1, we can see that most of our participants actually significantly got cyber sick, and there were like significant difference in the total SSQ score and the nausea score, oculometer score, and also the disorientation score. And we also compared like when the participants say that they were sick as compared to when they reported that they're not feeling sick. And we find out that their physiological data was significantly different when they say that they were sick as compared to when they say that they were not sick. So based on that, motivated by the physiological data, we actually proposed this approach. So we have this VR simulation in here, and we collected the physiological response and also the verbal feedback on the fast motion scale. And we labeled the data, and then we processed the data. And then we have some deep neural network or deep neural classifiers in here. And then finally, we classify the severity of the cyber sickness, either in time, that is the detection, or either 2 minutes in future, that is the prediction. So we got this heart rate, breathing rate, heart rate variability, and the GSR data. We normalized the data. We detected the outliers, and we extracted 4 different features from each one of those data. So it turns out like we finally got 16 different features. The 4 different properties that we collected from each one of these data is that we collected their running average, we collected their percentage of changes from the resting baseline, we collected their minimum value and also the maximum value. So within that 3-second sliding window. Instead of considering the raw data, we considered a 3-second sliding window. So within that 3-second sliding window, we actually got this 4 feature. And from those 4 different data, we got 16 features that we finally did a correlation analysis, and we find out that a couple of these features are not significant, so we get rid of that. And we proposed, or we actually used 4 different types of classifiers. So the first one is the support vector machine classifier. The second one was the long short-term memory classifier. The third one is basically a coronary artery disease prediction. That is a combination of convolutional neural network and LSTM classifier that people used for coronary artery disease prediction. And we used that one because we actually used heart rate data, so that makes sense. Finally, we proposed our own CNN and LSTM classifier that is much simpler and that is more specific to cyber sickness. And this is an overview of that architecture. So we have a CNN layer to extract the feature, and then a couple of LSTM layer to get the temporal data from the data. And then we finally predicted the severity class. So we have pretty good results with our data. For the detection, we actually got 97.44 with our proposed CNN LSTM model. And for the prediction, it was like 87.38% of mean accuracy. And this is the result for a 5-fold cross-validation. So to conclude, yes, we can detect and predict, and we can automatically detect and predict cyber sickness without any kind of human intervention, because the model that we just developed, you can basically deploy that, and then that should be okay to detect and predict the class of the cyber sickness severity. Is that there are some limitations. The problem with the current data is that it needs more features. We only consider physiological data. There are each data or there are some video data that is also correlated with cyber sickness. So we need to consider into that. And we need to basically, based on the severity, we need to basically apply some reduction technique during the simulation so that we can elevate the discomfort. Of course, we need a diverse demography to test our approaches in different demography and different virtual environment other than roller coaster. So that's our future work is, and that's the conclusion of our work. And if you have any question, please contact with me, and I'll be happy to answer with you or set up any personal meeting with you. So until then, stay safe, and thank you for listening.
Great. Let's give a round of applause. Ricardo, thank you. Okay, I think there was a question among the audience. So looks like the scene you've been using is basically the roller coaster scene usually causes a lot of cyber sickness. How do you think that the findings from that type of particular scene could be generalized to other VR environments?
Yeah, so the main target of our study was to evaluate the automatic detection and prediction. So we wanted to make sure that the participant got sick. So that's one of the motivation for using that roller coaster simulation. And I completely agree with you that it needs to be tested with a more generalized sample size of the usual simulation that happens in a typical virtual reality experience, to test this model or this type of approach with a sample size of that kind of generalized version. So that needs to be yet tested, and we are planning on to basically run future studies that's going to happen, that's going to have a lot more sampled version of different types of VR interaction and VR simulation. So that's our future goal is. So yeah, I'll be waiting to see what's going to happen when we were trying to generalize this thing. So this target for this paper was not generalization. It was just to propose the automatic detection and prediction of cyber sickness.
Thank you. I think we have a bit of time to have one more question if there's any burning questions from the audience. If not, maybe I'll ask a quick question.
Yeah,
so
sure.
I think you were also trying to predict
Yeah.
cyber sickness. And is just to clarify, was that prediction tested with the same set of participants, or was it? Are you planning to test it with other participant pool, or how is that going?
Yeah, so during the training set, the participant differs from the training set and the testing set. So those are like different participants in training versus the testing. And yeah, we are planning on recruiting more participants, especially from different demography, and recruiting more female participants to test result on more generalized population. So one of the reason I believe that the accuracy was a little bit biased is because that we have a roller coaster simulation and the participant was pretty specific. So in order to generalize, I really I really agree that we need to recruit more diverse population and diverse simulation.
Okay, thank you. Just
Sure.
one last question from Hoba. Professor Steve Feiner posted, have you thought about how your predictions would hold up for exposure over a series of sessions?
Yeah, so that actually, so if I do series of session, so the first thing to consider is that how much time is going to be like in between those series of sessions. So if they are like consecutive series of sessions, so one session might impact the other session. If they are like a couple of weeks apart, then there might not be that much of correlation between the consecutive session. So that is something that we also should consider. In this particular study, we haven't actually considered that, but yeah, that's a nice question. That's something that we should look into.
Okay, thank you very much. I think because of the time, in terms of time, let's thank again Rifatu for his presentation and question and answer. Thank you very much.
Thank you.
And please, I think the Hova will be still open. So if you have any other questions, please feel free to post it to them, and the authors, please check them after the session and try to engage with the audience as well. Thank you very much. So we'll move on to the next paper. We're going from cyber sickness to a slightly different topic. The third paper in this session is titled Seamless Bidirectional Transitions Along the Reality-virtuality Continuum, a Conceptualization and Prototype Exploration. The paper is from a group from LMU Munich, Germany, and the authors are Sinu George, An Tien, and Heinrich Hassmann. And the paper will be presented by Sinu George, who's joining here today. And thank you for joining the podium, and we'll play the video now. Thank you.
Hi everyone, I'm Sinu George from the LMU in Munich. I will be presenting our paper today called Seamless Bidirectional Transitions Along the Reality-virtuality Continuum, a Conceptualization and Prototype Exploration. Before we move on, I'd like to introduce you to Lucy and Tom. Lucy is wearing a head-mounted display and Tom is working on a laptop. They're both working in this collaborative context. My research over the last years has been in this specific context. Prior work has established that ubiquitous devices create a disconnect between the virtual and the physical reality. However, this disconnect is heightened with HMDs, as the HMD user, in our case Lucy, cannot see the physical reality at all. So the aim of my research is basically to reduce the disconnect between the realities. To summarize, we want to reduce the disconnect by treating both environments equally, the physical and the virtual reality, such that the user is aware of the real environment, the physical reality, while in the virtual environment or the virtual reality, and vice versa. We envision users to do so without taking the headset off, which we refer to as seamless transition. We build our work on Milgram's reality-virtuality continuum, where he basically defines different states and in-between states that users can be in across from the physical reality all the way to the virtual reality and back. So we are interested in users going from the physical reality to the augmented reality with the same interaction paradigms as they go from the virtual to the augmented virtuality. To summarize our research, in research question 1, we're looking at what dimensions make the design space for seamless transition concepts. And in research question 2, we're looking at how do users interact with such a seamless bidirectional transition solution. The rest of my talk would be structured in these 2 research questions, going from the design space in RQ1 to the prototypes in RQ2. So the design space in RQ1, we used expert and novice interviews and a story completion method, where participants were given a beginning of the story, where users were collaborating, and they were asked to complete the rest of the story. We used thematic analysis to come up with the dimensions of the design space, and we also added the solutions that participants provided into the design space dimensions. So our contribution here is design space for seamless bidirectional transitions in co-located settings. Our design space consists of 3 dimensions. On the top, we have the motivation for transitioning. On the left, in D2, we have availability. In D3, we have modality. So motivations can be for social interaction, for physical integrity, so there is no harm happening to your body, for just being aware of doing interactions on physical and virtual objects. For availability, we split up into user-triggered, system-triggered, and continuous. And then there are different modalities that we can use to actually transition. Today, we don't have time to go into the details of the design space. However, I'd like to focus on 2 gaps that we've identified, specifically for user-triggered solutions that enable physical integrity and interaction with physical objects. We've done a couple of iterative ideation sessions where we created prototypes. And with this, we're moving on to the second part of this presentation that covers RQ2. And I'd like to introduce you to one specific prototype that we're also discussing in the paper. Specifically, I'd like to introduce you to our virtual phone metaphor. So here we're using the virtual phone as a metaphor for peeking into the other reality. So peeking into the other reality is not necessarily a new concept. However, introducing the mobile phone as a metaphor and as a tool to transition is interesting in the context of bidirectional transitions, as it takes something that users already use to transition into a form of virtual reality and leverages that understanding and the interactions that come with it to transition to our parallel environment that's running. So we can transition here from the virtual reality to the augmented reality, and in the same way from the physical reality to the augmented reality. So this metaphor already affords interactions such as zooming in and out of the reality, tapping to draw attention to something, and interacting with virtual objects. So we've created a first lo-fi prototype of this metaphor that enables the user to transition bi-directionally. So from the real environment to the augmented reality in the same way and with the same interaction modality as from the virtual environment to the augmented reality. So we actually tested the virtual phone in a user study. In a within subjects lab study, we explored whether participants are able to use our solution of the virtual phone to complete bidirectional transitions. And we compared the virtual phone to another one of our prototypes that we're also presenting in the paper, but we don't have time to go into the details of that prototype, which we call Sky Portal. And we use the baseline, for the baseline, we use the front-facing camera of the HTC Vive. We use this statistical analysis and observations, which we also analyzed to discuss the applicability of the virtual phone for transitions. Specifically, we measured things such as presence, performance during the search task that participants had to perform while using the virtual phone concept. And we also had a questionnaire. So our contribution here is the virtual phone as a prototype, and also an extensive discussion for how to extend this prototype. Now going straight into the results, the participants perceived the virtual phone as an upgrade rather than an only solution. There were no significant differences with regard to presence between prototypes, suggesting that transitions are possible without affecting presence. The virtual phone performed much better than the Sky Portal. There were less collisions with the virtual phone in both directions. And we discuss design considerations such as the placement of participants after transition. So if we perceive both realities to be running parallel for the virtual reality, when you're going back into the virtual reality, you can actually think about considerations such as where to place participants, either where they left off or at a static place where they always return to. Due to the time constraints of this presentation, I'm not going to go into the details of our discussion. Please refer for that to the paper. So on the left, you can see here a current prototype of the virtual phone metaphor, where we are actually peeking into the virtual reality here. However, the solution works in both directions. So it's possible to actually tap, provide directions in both directions, and interact with the objects, of course. So for future work, we want to understand how to transition seamlessly between environments, because certain interactions may be safer or easier in one versus the other. And we are also discussing in the paper whether we need to redefine success measures for co-located VR experience, as we are specifically also talking about physical integrity and the safety of the user that's transitioning. Thank you very much for listening on our talk for the paper Seamless Bidirectional Transitions along the Virtual Reality Continuum.
Great, thanks. Let's give a round of applause to thank the presenter, please. Thank you. Okay, we have a bit of time to have a question and answer. Maybe I'll start with question. So I think in the presentation you briefly mentioned, because of the time constraint, not to mention the second approach. Could you briefly explain what was that?
Yeah, sure. The second approach was, we refer to it in the paper as Sky Portal, and it's basically a view also into the parallel reality. That's, yeah, if you look up, you basically see a view into the other reality. So it's not directly in your field of view. When you're walking through the environment, you have to directly look into it by looking up into the sky, basically.
So how did you pick those two methods? Was that based on the thematic analysis, or is that how was those ideas generated?
Yeah, we did. It was an iterative process. So we had some gaps that I pointed out, or that I point out closer in the paper as well, that we identified. And based on these, we took basically these gaps as starting points to iterate over solutions. So that was one direction that we took. And the other direction was that in the interviews that we did, participants actually provided solutions themselves. So we also included those in the ideation sessions. And these two are the most promising ones that we decided on.
Great, thank you very much. Is there any questions from the audience? Not, let's thanks again the presenter, Sino George from Alumni Munich. Thank you very much, Sino. Okay, thank you. So we'll move on to the fourth paper. The fourth paper is titled Towards Real-Time Recognition of Users' Mental Workload Using Integrated Physiological Sensors into a VR HMD. And it's a work from IRTBCom and University of Rennes in Ria. And the authors are Tiffany Long, Nicholas Martin, Anais Raisin, Ferran Argeloit, Jean-Marc Devers, and Anatole Lesueur. And today we have a presentation by Tiffany Long. We'll roll the video now. Thank you.
Hello everyone, my name is Tiffany Long, and today I'm going to introduce you our work on mental workload operations in VR in real time using physiological sensors integrated into VR. So mental workload is a very popular metric in many fields because it has shown to impact users' well-being and users' performances. So it can be especially interesting to try to assess users' mental workload in VR in real time to make them more adapted to users. So there are different ways to measure mental workload responses in real time. So you can use, for example, physiological measures, behavioral measures, or task performance measures. And one way to go back to the psychological processes, so one way to predict and to measure users' mental workload is to use these measures and machine learning algorithms. So there have been some studies which try to recognize users' mental workload in VR using, for example, brain-computer interfaces and physiological sensors. There have been more and more companies and studies which also try to integrate the physiological sensors directly into the VR HMD. However, none of them will propose the real-time recognitions of users' mental workload using these HMD sensors in VR. And our first objective today is going to propose an all-in-one approach to do the real-time recognitions of users' mental workload in VR using physiological sensors integrated into an HMD. So we decided to use supervised learning to train the mental workload recognition models, and we wanted to compare different supervised learning setups and to see the effect of these setups on the mental workload recognition accuracy. So first, we wanted to see which sensor works best to recognize the user's mental workload. So we trained different mental workload recognition models using the sensors taken individually and using different associations of sensors. And we wanted to see which one was the most performant, so which one was the most important for the mental workload recognition model. We also wanted to check if integrating sensors directly into the VHMD impacted the mental workload recognition accuracy compared to using commercial grade sensors, so using here, for example, WIS sensors. And we wanted to compare different signal normalization methods. So how do we use, for example, the Bayesian data to improve the mental workload recognition accuracy? How do we take into account the user's physiological differences? So today, during this presentation, I'm just going to focus on presenting the all-in-one approach to do the real-time recognition of user mental workload. And I'm just going to present you the result of which sensor works the best with a small discussion. So how did we integrate the sensors inside the VR headset? So we used an electronic card to access data from multiple sensors, and we placed this electronic card inside the 3D printed case, which was modeled using CAD, and we placed this 3D printed case on the back of the VR headset. Here we decided to use the HTC Vive Pro Eye because it already had an eye tracker inside it. So we measured the user's cardiac activity using a PPG sensor, which was placed on one of the user earlobe. And we also measured the user's forehead ectodermal activity using two sensors, which were placed on the mouse inside the VR headset. So this is a very simple scheme of what we are trying to achieve. So as input, we want to have objective measures. So we want to have, for example, physiological data. We want to have, for example, task performance data. And as output, we want to predict the user's mental workload level. So in between, we need to have a mental workload prediction model, and to train it, we need to collect data. So this is our data acquisition protocol. So we ask users to pilot an aircraft in VR, and while the user was piloting the aircraft, sometimes they had to do a communication task and or a monitoring task. So we had 75 participants, and we collected several types of measures. So first, we collected physiological measures using the HMD sensors, using the commercial grade sensors, and using the micro-eye eye tracker. We also recorded the user's piloting task performance. So we recorded the distance to the trajectory the user had to follow during the data acquisition protocol. And finally, we also recorded the user's subjective mental workload score. So during the data acquisition protocol, we asked users to self-report their mental workload using 5 different ratings, 1 meaning that the user was underloaded, and 5 meaning that the user was overloaded. So to train the recognition model, we use the objective measures as predictor variables, and we use the subjective mental workload score as the target variables. So we did some signal preprocessing. So we synchronized the subjective mental workload score with the objective measures, and we extracted the features from the objective measures. So in the end, we had a data set where we had objective measures features, which were labeled using the subjective mental workload level the user self-reported. And we decided to use a random forest algorithm to train the mental workload recognition model based on the literature. So we used 10 independent tenfold cross validation to evaluate the recognition model. And here on the top, you can see the ground truth. So the mental workload level the user self-reported. And on the left, you can see the predicted mental workload level, so the output of the recognition model. So here we obtain an average recognition accuracy of 65%, which is not too bad because we had 4 classes. So random have been of 25%. So as you can see, when the recognition model was wrong, it was mostly in adjacent classes, which is very encouraging. So we wanted to compare different setups, and here I'm just going to give you the results of the different tests we led to find out which sensor was the most important to train the mental workload recognition model. So the proactivity features were the most important to train the mental workload recognition model, followed very closely by the epidermal activity measures, followed by the cardiac activity measures, and finally followed by the task performance measures. So I wanted to draw your attention on the fact that when we used all measures together, we had a recognition accuracy of 65%. And when we just took off the task performance measures, we only had a drop of 2.2% in the mental workload recognition accuracy. So it is quite surprising because task performance measures are some of the most popular measures when we are studying users' mental workload. And in our case, we also had a significant impact of mental workload on the user's task performances. However, to train mental workload recognition models, the task performance features didn't really help in that case. So this is in our context, so maybe it can change in other contexts. However, it is very encouraging because physical data are not as dependent. So maybe it could be possible to use the mental workload recognition model we train here in other contexts where you would have different tasks, for example. So how do we do the mental workload recognitions in real time? So we used the time windows of 30 seconds and we extracted the physiological features during these 30 seconds. And we used these 30 seconds to predict the user's mental workload using the recognition model we trained earlier. And we slided these windows using a 1 second step. So we updated the prediction of users' mental workload every 1 second using a 30 seconds time window. So here you can see the interface for the real-time recognition we proposed. So on the top, you can see the ectodermal activity in real time. You can see the cardiac activity using the PPG sensor, which is also assessed in real time. And you can see the pupil dilatation using the Viper II tracker. So on the right, you can see the mental workload predictions, which is updated every 1 second. So you can see the 4 mental workload classes we decided to predict. And you can see the mental workload recognition accuracy for each of these 4 classes. In conclusions, we propose an all-in-one approach to the mental workload recognition in real time using physiological sensors integrated into a VRHMD. And we had very encouraging results to use the physiological sensors integrated into a VRHMD. And we found out that task performance didn't really help in our case to train the mental workload recognition model. So it would be very interesting to try to assess the different brain signals, for example, the FNIRS or EEG, and to compare the signals to the physical sensors we have for the mental recognitions. We could try to use the recognition model we trained here in the piercing task in other view applications where we would have different interaction constraints, different contexts to see if it can be generic. It could be very interesting to try to exploit the recognition models we have here to adapt inertial virtual environments in real time based on users' mental workload to make the virtual environment more adapted to users. So thank you for attention, and if you have any questions, please feel free to ask them to me or to Nicolas Martin, who is also there today during this session.
Great, thank you for the presentation, and let's thank the moderator. Thank you. Got a question on the I've got a question on the chat box from Rifato asking, what are the features you are considering from the eye tracking data?
That's a very good question. So we use the features from the literatures. So basically, we use features linked to the pupil diameters, the pupil constrictions and dilatation speed, and the pupil amplitude. So you can find more detail in the paper about it, but yes.
Thank you. I understand you've been using multiple different sensors. Have you also looked into comparing which sensor is the most best predictor, or was there any exploration in that direction?
Yes. So in the paper, we train different recognition models, and we compare the recognition model using the sensors taken individually and different association of sensors, and we compare the recognition accuracy we obtain using these different models. And basically, the ocular activity was the best sensors to recognize users' mental workload in our case, followed very closely by the epidermal activity and followed by the cardiac activity. And task performances didn't really help a lot in our case to predict the user's mental workload.
Thank you. Is there any questions from the audience? Not, let's thank the presenter, Tiffany, again, and thank you very much.
Thank you.
Okay, our last paper we have in this session is titled Evaluating Mixed and Augmented Reality, a Systematic Literature Review from year 2009 up to 2019. This is a paper written by a group of researchers at University of Stuttgart and Graz University of Technology. The authors are Leonel Marino, Magdalena Schwartz, Matthias Kraus, Michael Sedlmeier, Dieter Smastik, Daniel Weiskopf. And today we have the presentation by Leonel Marino. And thank you, Leonel, for coming up to the podium. We'll play the video now.
Welcome to my presentation. My name is Leonel Merino, and today I will present a paper titled Evaluating Mixed and Augmented Reality, a Systematic Literature Review, 2009-2019. In this paper, I had the collaboration of Magdalena Schwartzel, Matthias Kraus, Michael Sodelmayer, Dieter Schmalstig, and Daniel Weiskopf. In this table, I would like to summarize related work that investigated various aspects of evaluations in mixed and augmented reality. In contrast to previous work, in our investigation, we include a higher number and more recent publications and focus on a comprehensive view of evaluations. That is, we focus not only on user evaluations, but also on the evaluation of techniques. We collected relevant papers from the main venues in mixed and augmented reality published between 2009 and 2019. Consequently, we collected 296 papers from ISMAR, 88 papers from CHI, 46 papers from IEEE VR, and 28 papers from UIST. Then, we classified the 458 papers found into one of 5 types. We classified 277 technique papers that present new algorithms, for instance, to improve performance. 130 evaluation papers that elaborate on judgments of the quality, importance, or value of mixed and augmented reality approaches. 6 model papers that correspond to documentaries, formalisms, and taxonomies. 15 system papers that discuss design choices of the architecture of a system, and 30 design study papers in which authors present the use of existing techniques to address a relevant problem. For each paper, we identified a main research topic. In the end, we collected 16 different topics. Although multiple topics might overlap, we think that our classification can help identify new emergent topics. We classified evaluations using 7 scenarios presented in the literature of visualization. The scenarios identify the context in which evaluations happen. Notice that multiple scenarios can be identified in a single evaluation. We identified 179 evaluation scenarios that involve a qualitative discussion of results. 202 scenarios that involve evaluation of algorithm performance. 179 evaluations of the performance of users. 183 scenarios in which evaluation considered aspects of user experience, and a few other scenarios that involved assessment of collaboration, communication, and understanding the implications of adopting mixed and augmented reality into a working environment. For each paper, we also extracted specific methods that are used in evaluations to analyze specific human aspects that deal with cognition. We use these methods as a proxy to identify cognitive aspects that are involved in evaluations. In the end, we found 10 cognitive aspects. Finally, we analyzed 2 aspects of the configuration of user studies. First, we identified if evaluations were conducted in a laboratory setting or in the wild. And second, if participants in studies were static or in a mobile fashion. We found that a majority of evaluations are conducted in a lab with participants in a static fashion. As a summary, we present here an overview of the relationships of our classifications across the various dimensions. Next, we present considerations of cross-cutting concerns that emerge from the analyzed dimensions that can guide researchers to design evaluations in mixed and augmented reality. The following line chart presents the evolution of evaluation scenarios. In the chart, we identify three main groups of scenarios. Scenarios centered in evaluation of techniques, which are in blue tones at the top. User-centered scenarios in red tones in the middle. And evaluation scenarios that involve teams in green tones at the bottom. Consequently, we call researchers in the field to complement the results of benchmarks with user studies when techniques involve a user interface and the combination of evaluations contributes to the research question at hand. We observe that questions that are addressed through mixed and augmented reality across multiple topics can involve various cognitive aspects. Therefore, we call researchers in the field to involve multiple cognitive aspects that are suitable to comprehensively examine a given research question. The following scatter plot shows the distribution of user studies based on their population and the percentage female participants involved. In the chart, we observe that often populations in user studies exhibit unbalanced genders. Therefore, we call researchers in the field to involve an adequate participant population with a more inclusive and gender-balanced distribution. We found that rarely user evaluations are conducted in the wild, that is the target environment of a mixed and augmented reality approach. We call researchers in the field to increase ecological validity by conducting in the wild evaluations with mobile or static participants depending on the target user behavior. We now discuss considerations for newcomers to the community who might be interested in knowing what types of work are mostly accepted at these venues. The chart presents the numbers of papers split by venue across research topics. We observe that ISMAR has interest on techniques that involve tracking, reconstruction, displays, and rendering. However, there is also an important number of papers that focus on design and human factors. As expected, the main focus of interest in CAI are design, human factors, and HCI technologies, as well as multimodal interfaces. We observe certain similarities in the focus of interest between ISMAR and UAST, and between CAI and IEEE VR. However, we observe the evolution of topics of interest, and we notice that in overall, there is a decreasing number of publications that focus on techniques and an increasing attention on user-centered research. With this slide, I would like to summarize my talk. I presented our work titled Evaluating Mixed and Augmented Reality, a Systematic Literature Review 2009-2019. My name is Leonel Merino, and I thank you for your attention.
Great, let's give a round of applause to the presenter. Thank you. Great, so we have some time for question and answer. Is there any questions from the audience? Great, maybe I'll ask questions. So according to your survey, it definitely looks like it's about time to go into the wild and also dig deeper with qualitative analysis. Is there any particular type of study or study technique that you would like to recommend based on your survey?
Thank you for the question. Not really. I think there is a type, but in general, probably moving forward to conducting in the wild studies could be a good decision.
You. There is one question from Hova. So it is interesting that you considered gender bias in the demographics. Have you also considered bias as to age, disability, or other demographics as well?
I think we collect some data regarding other demographics. I'm not sure those are reported on the paper, but yes, I think in the paper basically we all report the gender.
Okay, thank you. Any other questions from the audience? That I might just maybe have one more question. So thank you very much for presenting that nice literature review paper. And I think there's a lot of effort goes into this type of systematic review. If you would like to share some tips with the future authors of this type of systematic review papers, what would it be?
Indeed, it was quite some effort. I think one important thing is about establishing concrete and explicit criteria to classify all the data that you want to extract from papers. Probably that would be the main one. We revise some previous taxonomies. At the end, we define some new categories in some of them. So we adapt them based on some data that we collected in the beginning. Yeah, I think that would be my main advice.
Great, thank you very much. I think in the chat box there is quite general question asking, is there any recommendation to create a good user experience questionnaires, or what would be the best method if you have any experience in that?
Yes, we found really a large number of different questionnaires used to analyze various aspects of user experience. It's not so clear. I think at the end, what you need to do is to tailor your questionnaire to the specific research question you are addressing. And to do that, probably you might want to involve different questions from multiple questionnaires.
Great. Thank you very much. I think there is one person from the audience raising hands.
Yeah, I was wondering. Hi.
Yep, thank you.
I was wondering what exactly the inclusion criteria for the papers were that you chose.
So we included full peer review papers from these four main.
Sorry, I think Leonel, you might have been muted.
Oh yeah, I didn't.
Sorry about that. Yeah.
Yeah, I think that the inclusion criteria was about accepting in the study full peer review papers from these four main venues. I think we also included some short papers. Yeah, that was it.
Okay, I think one last question from the chat box. Do you think there is too many different questionnaires?
Indeed, I think it's clear. Well, it depends. In some of the specific cognitive aspects, we see some standard de facto questionnaires. But in some others, we found that there is not clear guidance regarding which questionnaires would be more suitable. and the result is that there are so many questionnaires being used.
Thank you very much. I think we are just about to time to wrap up this session. So let's give another round of applause to Leonel and also the other presenters in these sessions as well. Thank you very much. So thank you very much for the presentations to the authors, and also thank you very much for all the audiences joining this session. This is conclusion of session 12. Thank you very much.
Thanks, Professor Gandhi, for this great session. We are going to have a small break right now. Please take some water, take some coffee. We're going to come back in 13 minutes, okay? Try to interact, to discuss a bit. See you then. Thank you.
Hello.
Hello.
Hi. Yeah, nice talk and nice work.
Yeah, thanks. You too.
Yeah,
Yeah, we
sure.
have very similar works.
Yeah, Dr. Nicola. Yeah, very nice work. Yeah.
Thank you.
Yeah.
I don't know if Nicola can hear us. I think he
Oh.
has some emergency or something.
Okay.
So, yeah.
Welcome to the iLearn Virtual Campus. Please sign up for a free iLearn membership on our website, check out our 7th annual conference coming next spring 2021, and let us know if you're interested in hosting events or leasing space on our campus by emailing campus@immersivelrn.org.